Hello and welcome to this lesson on the derivative function. I'm Mohamed Kadam Kahe. The PDF of the lesson is available at the website I indicate here. The outline of the lesson will be firstly to define the derivative, then to state its basic properties. After that, I will present the notion of table of variations. The fourth section concerns the equation of the tangent line. The final section applies the derivative to calculate a limit. I will show you that the derivative may be very useful to calculate some limits. So let's begin by defining the derivative. A function admitting a derivative is called differentiable. So a function will be said to be differentiable if its curve is smooth, such as the red curve here. The green curve at point 0 is not smooth, so it is not differentiable. That is to mean it doesn't admit a derivative at this point. So the intuition is that a function is said to be differentiable if we can draw its curve smoothly. That is to say, without changing the direction suddenly. And the mathematical definition may be formulated as follows. We say that a function f from the set of real numbers to itself is differentiable at a point a if the limit when x goes to a of the ratio f of x minus f of a divided by x minus a exists and it is finite. We then denote this limit f prime of a. So f prime of a is by definition the limit of the ratio given in this box. And call f prime of a the derivative of f at point a. We shall name or denote this ratio the rate of change of f between the point a and the point x. Okay, so the derivative is the limit of the rate of change of f when x tends to a. Here is an example. Consider the function f which is equal to x squared. So let's try to calculate the limit of this ratio here. So we replace f of x by x squared, f of a by a squared, and by a remarkable identity, this ratio here equals x plus a, and the limit of this sum when x converges to a is 2 multiplied by a. So f is differentiable at this point a, and the derivative equals 2 multiplied by a. So you see that applying the definition, we can get explicitly the derivative and prove that the function is differentiable by checking whether this limit exists. In practice, we shall use some basic properties of derivative to avoid to go back to the definition each time. For example, this is a useful theorem. All polynomial functions, such as x, x squared, or any combination of the powers of x are differentiable. Note that a continuous function is not necessarily differentiable. Here is an example. Consider the function absolute value of x, whose curve is like that. Okay, I've shown it in the beginning of this lesson. This function is continuous at point 0, but it is not differentiable. Indeed, if we consider the rate of change between 0 and x, it is equal to absolute value of x divided by x. The limit of this ratio on the right of 0 equals the limit of x divided by x, because on the right of 0, absolute value of x equals x, since x is positive. So the limit will be 1. Whereas the limit on the left equals the limit of minus x divided by x, since x is negative, so it equals minus 1. Hence, absolute value of x divided by x does not have a limit at 0. So the function f is not differentiable at point 0. On the opposite side, a differentiable function is necessarily continuous. Indeed, since the f prime of a equals this limit, and this limit exists and is finite, then we can write the difference f of x minus f of a as x minus a multiplied by the rate of change. But the rate of change converges to f prime of a, whereas this term here goes to 0. So the product will go to 0. Then the limit of f of x equals f of a when x converges to a, and this shows that the function is continuous at point a. The following theorem is very useful in practice. It concerns the sum, the product, and the ratio of differentiable functions. Let's give the precise statement. Consider two functions f and g to be differentiable functions. Then for any real number c, the function c multiplied by f is differentiable, and c f prime equals c multiplied by f prime. So you see that the constant may go outside here, and we get c multiplied by the derivative of the function f. Moreover, the sum f plus g and the product f by g are differentiable functions. Moreover, the derivative of f plus g equals the derivative of f plus the derivative of g. For the product, the formula is a little bit complicated, more involved than the previous one. F multiplied by g prime equals f prime multiplied by g plus f multiplied by g prime. Please keep in mind this very useful formula. The ratio f divided by g is also differentiable at a if g of a is not 0. Moreover, f divided by g prime equals f prime g minus f g prime divided by g squared. Please also keep in mind this formula. A particular case when f equals 1 gives the following result. 1 over g is differentiable at a if g of a is not 0. Moreover, 1 over g prime equals minus g prime divided by g squared. These three formulae are very useful in practice, so please keep them in mind. The following table gives some very useful formulae also for derivative of usual functions. The derivative of a constant is 0. The derivative of x equals 1. The derivative of x to the power n equals n multiplied by x to the power n minus 1. So you can remember this formula by saying that the power here n falls down, and then we subtract 1 from the power. The derivative of 1 over x is minus 1 over x squared. The derivative of square root of x is 1 over 2 multiplied by square root of x. Observe that we can find certain derivatives from that of the power x to the power n. For example, 1 over x may be written as x to the power minus 1. So the derivative may be found by applying this formula here, which gives minus 1 multiplied by x to the power minus 1, which gives minus 2. So it is minus 1 divided by x squared, and we retrieve this formula. I show you a second example. The square root of x may be written as x to the power 1/2. So if we apply again this formula to this power, we get 1/2 multiplied by x to the power minus 1/2. So this gives 1 divided by 2x to the power 1/2, which gives exactly this formula here. Another example, consider the function 1 divided by square root of x. This may be written x to the power minus 1/2. So the derivative, by applying again this formula, is minus 1/2 multiplied by x to the power minus 3/2. And this gives this result for the derivative of this function. So you see that the derivative of the power is very useful in many cases. We now state a theorem about the composition of two differentiable functions. Here is the statement. If u is differentiable at some point a and v is differentiable at u of a, then the composition v with u, like this, is differentiable at point A. Moreover, the derivative of v composed of u equals firstly the derivative of u, then the derivative of v applied to u of x. So we shall together keep in mind this formula, but saying when I differentiate the composition, I firstly differentiate this one, which is interior here, and then we differentiate the function v, which is exterior, and apply it to the first function. Okay, so try to keep in mind this formula. It is very important in differentiation. Let's apply this formula to calculate the derivative of h of x, which equals this expression here. So we consider first u, the function given by this polynomial. Its derivative equals 3 multiplied by x squared. Moreover, the function v, which is the square root of x, is differentiable also, and its derivative is given by this expression. Then the composition, which is our function h, is also differentiable, and its derivative is given by, firstly we have to consider the derivative of u, which is 3 multiplied by x squared. Then we have to consider the derivative of v, which is 1 divided by 2 multiplied by the square root of the function in the interior, which is given here. Okay, so this is an application of our theorem. A consequence of this theorem, very useful in practice, is this table. In the first line I give a function f, and in the second line its derivative. So if the function f is in the form some function u to the power 2, which is differentiable, then the derivative equals 2 multiplied by u multiplied by u prime. So how does this work? We consider u as a variable. So if it was x squared, then the derivative is 2 multiplied by x. So this is the first term. And then we add the corrective term, which is u prime. And you see in this table that this correcting term is always the same. Okay, so u prime will always be the correcting term in my formulae. For example, if I differentiate u of x to the power n, it will give n multiplied by u of x to the power n minus 1. So as if I differentiate x to the power n, and then I add the correcting term u prime of x. In the same way, the derivative of 1 over u will be equal minus u prime divided u by u squared, since the derivative of 1 over x is minus 1 divided by x squared. So this is the first term here, comes from the fact that it is 1 over x, and then the correcting term is always the same. Similarly, the derivative of square root of u will be u prime divided by 2 multiplied by square root of u. So you see that all these formulae may be retrieved, reminding the corresponding formulae for the power of x, and then adding the correcting factor u prime. Try to keep this in mind, it is very important in exercises. We move now to the section about the table of variations. So here is the fundamental result, the variations of a function f from the sign of its derivative. Let f be a differentiable function on an interval a, b. If f prime is positive, then the function is strictly increasing. If f prime is negative on the interval a, b, then the function is strictly decreasing on this interval. So an application of the theorem to this simple example, let f be the function given by this expression here, then its derivative equals 2 multiplied by x minus 4, which equals 0 for x equals 2. So we begin by the first row where we put x which varies from minus infinity to plus infinity. Okay, so this is the first row of my table. Then at point 2, the function f prime will be equal to 0. It is negative in the left and positive on the right of the point 2. And the variation of f consequently are given as follows. On the left of the point 2, the function is strictly decreasing, and on the right, the function is strictly increasing. In particular, this table shows that the function f admits a minimum here at point 2. That is to say, the function f of x is larger or equal than f of 2, which equals minus 1. And indeed, this result may be shown directly, since f of x plus 1 from this expression here equals this polynomial, which is precisely x minus 2 squared, which is a positive number. So f of x is larger or equal than minus 1. Let's give now the equation of the tangent line to some curve of a differentiable function. This is the theorem given this equation. If a function f is differentiable at some point a, then its curve admits a tangent at point a with equation given by this expression here. Okay, so let's make a figure. This is the curve of the function f. Okay, c of f. And I consider some point here, and I give here the equation of the tangent line t at this point a. So it is given by f prime of a multiplied by x minus a plus f of a. Observe firstly from this equation that for x equals a, this term here vanishes, okay, and we get y equals f of a. This is normal since the tangent meets the curve of f at the point with coordinate a in the abscissa and f of a in the ordinate. Okay. Moreover, the slope of a straight line, say d, with equation y equals p of x, multiplied by x plus q, is precisely this coefficient p. Observe in this case that when the abscissa x increases by 1, the ordinate one y increases by p. So this is interesting to get the slope from the curve of the line. Here a way to retrieve the tangent equation if you forgot it. So remind that the slope of the tangent is equal to the derivative. So we start by writing the equation like this: y equals f prime of a, which is the slope, multiplied by x, and we prepare the continuation of this equation by making brackets here. So we say that we know that when x equals a, y equals f of a. And this is how we can retrieve the equation of the tangent to the curve. Let's apply this result to this function here, which is a polynomial. Its derivative equals 2 multiplied by x minus 4. And in particular, for the point 4, f takes the value 3, and the derivative equals 4. So the curve of f admits a tangent at point a equals 4 of equation y equals, so the derivative which equals 4, okay, multiplied by x minus 4 plus the value of the function which equals 3. So we get 4x minus 13. And this is the equation of the tangent at point 4. So here is an illustration of the example I treated in the previous slide. The function f is plotted in red here, and the tangent is in blue. So this is the tangent line. At point 4, the function takes the value 3, so it is okay. Observe moreover, then we move to the right in the abscissa by 1. Then we have to increase by 4 to get a new point on the line, and this is the slope of the tangent at this point. Okay. The tangent equation is here, so the slope equals 4. I will show now how to apply the derivative to calculate a limit. So assume that we aim to calculate this limit here. So it is the limit of the ratio of two polynomials when x goes to 1. Observe first that it is an indeterminate form since it gives 0 divided by 0. So let f be this function here, x power 3, then the derivative equals 3 multiplied by x squared. Observe that this quantity here may be viewed as a rate of change, and this is the fundamental point. So this ratio may be seen as f of x minus f of 1 divided by x minus 1. And this is precisely a rate of change. So the limit of this rate of change when x goes to 1 equals the derivative, which is f prime of 1, and this derivative equals 3 multiplied by 1 squared, which gives the value 3. So the limit of our ratio of polynomials equals 3. Okay, that's it for this lesson. I hope it was clear and useful for you. Have a nice day and see you in the next lecture. Goodbye.